Hello, this is my fourth or fifth time recording this, and I'm getting tired, but I'm going to start with metallic bonding. Metallic bonding, for example, you can do this with any metals, but I'm going to use magnesium. If we look at the electron configuration, the orbitals, you should see it is 3s2, which means there are two electrons in the 3s orbital. And these s orbitals come together and they form a molecular orbital, which is an area in which the electrons in this orbital are delocalized and can basically wander around. This leaves charged nuclei of these atoms, which attract these delocalized electrons and create the force that holds the molecule together. So with magnesium, for example, you have a twice as much force holding it together than, for example, with sodium. And the reason for this is because since you've lost two electrons, which is what is in the top orbital, you know that the nuclei of these atoms have a 2+ charge rather than a single +1 charge. And you also know that there are twice as many electrons, so there's twice as much force being generated. Second type of bonding we need to take a look at is covalent bonding. I'm going to use hydrogen sulfide as an example, which is H2S. Sulfur, since it is in the 6th group, which you can see from this periodic table, forms two bonds. These two bonds are formed with hydrogen, which is in the 1st group. We can also look at the electronegativity. Sulfur has an electronegativity of 2.5. Hydrogen has one of 2.1. This means there is a 0.4 polarity, which means it's covalent. Since sulfur has a higher electronegativity, is delta minus, and hydrogen is delta plus, ordinarily an atom like this, in its bent shape, would thus be able to attract positive charged parts of atoms at the top and negative at the bottom. This is the reason H2O, water, is so attractive, because it has clear distinctions between the sides, and this is definitely polar. With other covalent molecules, however, for example, methane, I'm going to try not to say methane, Mr. Slater does, you don't have any charge, any polarity, because it is surrounded by delta positive atoms. There's no delta negative atom on the outside. That's not the case, obviously, with hydrogen sulfide. We can also look at the Lewis-Stott diagram. Sulfur has 16 electrons, which means it has 3 shells. The inner shell has 2 electrons, the second shell has 8 electrons, and the valence shell has 6 electrons. I obviously drew this wrong, as in the valence shell, you should see 1 electron from the sulfur each bonded with the 1 electron from the hydrogen in its valence shell, which is what actually forms the bond. And the clear reason for this, as demonstrated from orbitals, is that you form a hybridized orbital. Ordinarily, the sulfur's electron configuration would be 1s2, 2s2p6, 3s2p4. However, hybridized is 1s2, 2s2, p6, sp3, which contains 5 electrons and is bonded with the 2 hydrogen atoms. We can also look at ionic bonding. I'm going to use sodium chloride as an example. That's table salt. Sodium being a metal, and ionic bonding is always between a metal and a non-metal. Chloride is a non-metal. Chlorine, sorry. Or more specifically, a cation, a positively charged ion, and an anion, a negatively charged atom. The reason for this is because metals lose electrons, non-metals gain electrons. In this case, since the charge of any molecule, except for the polyatomic ions that we will look at next, is 0. So you have the same charges on either side. And this also, clear polarity means that ionic molecules have very high melting points. And the reason for this, again, is that each of these atoms attracts 7 other atoms, including the one that is already seen by the formula, that it holds together because it is a negatively or positively charged ion. Ion. To calculate the electronegativity, it is the same as covalent bonds, except rather than for covalent bonds, it is 0.4 to 2.0. Anything over 2.0 is ionic. The electronegativity value total of this molecule is 2.1, meaning it is ionic. So let us now look at polyatomic ions. We're going to look at sulfate, which is SO4 with a negative 2 charge. Polyatomic ions are simply molecules that have a charge, thus to form with other to form a complete molecule need to be bonded with other atoms. So because of this, the diagram I'm using is of sulfuric acid, which is a complete molecule. As you can see in this, if you imagine that the hydrogen atoms were not there, there are 2 bonds that can be formed, one with either oxygen at the bottom of this diagram, and each of these, as well as the other 2 oxygen atoms, which have double bonds to sulfur, have an extra bond that can be made, obviously. Okay, so this brings us to our final point, which is about generally naming creating formulas for molecules. With ionic molecules, the key is, first of all, to put cations before anions. So the cation is always the metal, which is positively charged. And this, no matter how many of these atoms there are, it is just a single name of it, unlike covalent formulas, which are different. The anion is last, and once again, it does not indicate the number of electrons, number of atoms. It simply indicates the atom. And instead of having the ene at the end, it is I. For example, chlorine becomes chloride, oxygen becomes oxide, carbon becomes I don't know. Okay. Anyways, this doesn't apply in a certain context, which is with, first of all, oxyanions, which are molecules that are formed with polyatomic ions that involve oxygen, such as sulfate. In certain cases where these polyatomic ions are formed with different numbers of oxygen atoms, the lower number of oxygen atom polyatomic molecule is polyatomic ion is ite. The top is sulfate. Sulfur only forms one type, so it's sulfate. There's no sulfite, but there are certain types. Oh, there is a sulfite. Never mind, I take that back. It's SO3 rather than SO4, which has the same charge of 2 minus. Also, if this is the same case with something that's not a polyatomic ion, for example, copper, which can either form an ion that is +1 charge, or it can form a 2+ ion. You indicate that with a Roman numeral I in parentheses after the copper, or Roman numeral 2 in parentheses after the copper as well. Okay, I'm pretty sure that's it. So thank you for listening. And that might have been a bit long. Yes, it was. But I tried to include everything, so